So we're going to talk about factorising polynomials, but to do this we're going to start talking about remainder theorem. The remainder theorem will help us to find factors of polynomials, and once we know how to find factors of polynomials, we can use those factors and our knowledge of division of polynomials to fully factorise polynomials, technically of any order, but ultimately if it's more than, say, a quartic, it's still going to take you a fair while. Just remember what I said yesterday in the calculator session, and for anybody who wasn't here, if you get a question that asks you to factorise a polynomial, there's no reason why you can't get your calculator, factorise the polynomial on there using the polynomial solver, so you know the x-intercepts. Have that knowledge of what the answers are before you start the question. No reason why you can't do that. So, and I would be encouraging you to do that. And to reiterate that other answer from yesterday, if you do choose to do that on the calculator, that's not an excuse for you to not show working and give me some sort of detail. So I will be exemplifying the working you'll need. So first, here's our page on factorising polynomials. You have factorised quadratics. More on that a little bit later in the lesson when we look at the formative task. You can also factorise a range of other polynomials using some simple techniques, which I'm going to show you now. So firstly, let's talk about the remainder theorem. Let's go number one. If f of x is a factor of p of x, so f of x is going to be a linear term in this case, so x minus 1 or x plus 7 or something like that. P of x is our polynomial, the big thing. So remember we defined p of x, q of x, r of x, d of x last lesson. P of x is our polynomial. Then that means that p of x divided by f of x will leave no remainder. So if it's a factor, there will be no remainder. That's something you need to do. And this is written mathematically, but it's hopefully from last lesson something that makes sense to you. This will be important later on. First, though, the remainder theorem. If we divide p of x by x minus alpha, I've written here, alpha is alpha. It's a Greek letter and it's just the standard notation for roots of functions. So we write x minus alpha. If we divide p of x by x minus alpha, then that means that the remainder will be p of alpha. Now this is a really simple procedure to find a remainder, but it looks hard as it is. When I get to the examples, it'll make sense. Additionally, if we divide p of x by this thing here, then the remainder is p of alpha over beta. So that's beta, and that's the coefficient of x. So I've got an example of both to show you. What does this mean in the real world? And I'm sorry if I move forward a little bit too much or too quick for those of you writing it down, but I can put it up later on. It is on the OneNote. And there's a note for you. The textbook uses p of negative alpha over beta, where it's b of x minus alpha, plus alpha instead of b of x minus alpha. So you just have to negotiate that. It just swaps those around, but you'll see what I mean. Okay. So let's have a look at the examples. Calculate the remainder. Sorry, I know, I've just moved on. People are writing stuff down. Calculate the remainder when p of x equals 3x cubed plus 4x squared minus 7 is divided by x minus 3. So what I've just stated above is that the remainder will be equal to p of alpha, which in this case is p of 3. So this is our alpha here, and it's 3. Now, think about it this way, and you'll have to go back to your knowledge on quadratics. If you factorised a quadratic and you had a series of factors and they were equal to 0, we would apply the null factor theorem. So we'd say these two things multiplied together equals 0. One of them must be 0. That would be applying the null factor theorem. And we might say in this case, therefore, that x minus 3, that's an equals, x minus 3 must equal 0. And then we would say x is equal to 3. That's where our alpha comes from. And that will be important later on, particularly with this question here. So that's where our 3 comes from basically saying, well, what if this equals 0? If it's a factor, it must, one option is that it equals 0. Now here's the easy bit. We've done the hard, complex, abstract, dealing with alpha, beta, stuff like that. P of 3 is really easy. P of 3 is equal to 3 times 3 cubed plus 4 times 3 squared minus 7. So this is remember that I work on function notation? If you get p of 3, we just substitute 3 in where x was, and then we evaluate. So this is 3 times 27 plus 4 times 9 minus 7. Obviously you would potentially have a calculator. 81 plus 36 minus 7 is 90. So if we divide p of x by x minus 3, the remainder is 90. You could do that division now and check. You should get 90 as your remainder. That's the procedure. The procedure is if you're given a divisor and you want to work out the remainder, this is the remainder theorem. You just put whatever alpha is in p of that number and it'll give you a remainder. Okay? Let's do that procedure again, but this time with our beta x minus alpha. So this is slightly different, and if you look back earlier to what I did above, you'll see that how that works. But I'm going to use this procedure here that I did in orange. This is the null factor theorem again. So if that is being divided, then the remainder theorem will come from letting that equal 0. 2x equals 3, x equals 3 over 2. And so to calculate the remainder, I'll just be a second, Harvey. To calculate the remainder, Rx will be equal to P of 3 over 2. That 3 over 2 comes from my calculation here. And that is equal to 3 times 3 over 2 squared, so cubed. And I will need somebody to help me with this. And I'm hoping maybe, Harvey, that's what you've done. Or you checked my first answer and it's wrong, perhaps. I don't know. Okay, could somebody calculate that for me, Harvey? Oh, you're calculating it.
So the first one,
yeah.
The calculator says 110.
110, you're claiming.
Yes.
Are you telling me that 81 plus 29 is 110, not 90?
Yes.
Seems feasible. Okay, I'm sorry. Good. Okay, second one. I know Harvey's onto it. Maybe somebody else is. Just a check. Reggie's onto it. Chris is onto it. Jackson's onto it.
73 on 8.
73 on 8.
Shouldn't it 3 over 2 be squared?
Yes, it should be. Sorry.
97 over 8. 97 over 8.
97 over 8. There you go, Harvey. You got it wrong, and it's all my fault. So sorry about that. Okay, yeah, there we go. 97 over 8. So be careful with what you're writing down. 110, 97 over 8. But can you see how easy that procedure is? That's the remainder theorem. Anytime it's quoted as the remainder theorem, you're just doing that to work out what the remainder is using the remainder theorem. Now I've got one more example there for you, C, and we're going to do this pretty quickly. It gives us a special result, which you might remember we talked about briefly earlier. So in this case, I've got alpha, oh, that's not alpha. Alpha is equal to 1, and so I get my remainder of x is equal to p of 1, which equals 3 times 1 cubed plus 4 times 1 squared minus 7, which is equal to 0. Now what do we say about the situation where the remainder is 0? With the remainder 0, there's no remainder, yes? So, say it louder for me, sorry. You might be leading on the right track, Chris. It's a factor. That's the figure I'm looking for, which I think you might have been trying to say, Reggie. So if we put in alpha and we get 0, there's no remainder. That means that this x minus 1 is a factor, because we can now write p of x is equal to d of x times q of x plus r of x is our form from earlier. And in this case, we get, 3x cubed plus 4x squared minus 7 is equal to x minus 1 multiplied by q of x plus 0, which we don't need to write on there. So that means this is a factor. We've just factorised. And the process, just because it seemed like a perfect time to mention it, the process you're going to follow now is, if you want to factorise a cubic or a quartic, we really won't ever go beyond quartic. And to be honest, in your exam, you're probably looking at cubics. You want to factorise a cubic? There is a cubic formula, which is like the quadratic formula. And I considered putting a screenshot of it on here, but it was so big that you wouldn't be able to see the letters from where you're sitting. It's a substantial formula. And so no one ever uses it. Instead, we get to here and go, I've got this this cubic here. I need to find an alpha that gives me a remainder of 0. And if I find that alpha, then I've got one factor. And now I've got one factor, I can use pretty simple polynomial division from last lesson, to work out what this quotient is, and then continue to factorise along. What type of function will this quotient be, by the way? Say it loud with pride. Quadratic. So quadratic, because a linear times a quadratic will give us a cubic. Okay? Now, let me show you something. And again, you've got that polynomial division. This is for some of you. You might be able to pick this up. So this is now a bit of an extension. And if you're not quite sure what I do next, then don't worry too much. But I do want to just show some of you. 4x squared minus 7. I would ask that you all at some point just check that you can do this polynomial division. Do that cubic divided by this to get what I'm about to get here for the quadratic. Because I know it's a quadratic, I'm going to write it down as ax squared plus bx plus c. And I already know some things about a, b and c. For example, I know that a must equal 3, because the only way for me to get 3x cubed is by doing this x times that quadratic term. So it must be 3 to get 3x cubed. Does that make sense? And I also know that c must be 7, because the only way to get this constant term is to do -1 times 7. And that gives me my -7. So I already know a and c are going to be really trivial in most cases. This is something that could help save you time on that polynomial division if the question doesn't specify what they want you to do. And b is a tricky one. So b is a little bit harder, it's in the middle, but bx times x will give me this quadratic term. So it'll be bx times x is bx squared, but I get -3x squared as well. So this -3x squared combined with the bx squared has to give me +4. And that tells me that the b must be 7 as well. And that then gives me 7x squared minus 3x squared, +4. You can expand this out and do this more technically and algebraically. It is the thing that we had set up in the OneNote the other day that I didn't cover. So example 5, you remember I talked about it. There is a method to do this that is more procedural, and there's a video here for that. So jump on there and have a look at that video if you want to. You don't actually need to know that. Okay? Anyway, what you need to know today is remainder theorem and what that means for factors. So here's the factor theorem. You got remainder theorem? Here's the factor theorem. If p of alpha is 0, which is what we said, so if the remainder is 0, then x minus alpha is a factor of p of x. And if p of alpha over beta is 0, then beta x minus alpha is a factor of px. That's the factor theorem, and it comes from our remainder stuff. If you prove that we have a remainder, then we transfer that remainder into a factor form. Then we get factors, and then you can use those factors with polynomial division to make things work. Okay? Which I'm going to do now, show that this, and you might get a question like this, where you're given the factor, and you need to show then fully factorised based on the first factor. The other type of question you might get is just, here's a cubic, fully factorise it. My advice again for you in that case would be, you're going to have to try and work out which alpha gives you a remainder of 0. It's probably going to be 1, 2, -1, -2. It will be something small. We're not going to put one that has 17 and expect you to find it somehow. Then, with this, what I would do is I would let it equal 0. Oh no, yeah, I'd let it equal 0, and I'd put it into that polynomial solver in your calculator. Put in 2, -7 and -2, solve it, and it will feed back 3 factors, because a cubic has 3 answers. One of them will be 2, guaranteed. And then you know which one it is, and then you might do a bit of cursory working and, you know, test 1, oh, that didn't work, test 2, oh, it worked, woohoo, and then off you go. So use your calculator to the best of your advantage. You may also get this in a tech-free exam though, so you have to be careful with that, which is why you need to still practice that testing. I'm going to zoom out a little bit because I know that some people are writing down the factor theorem. And I'm going to start example 7. Is that all right, Connor? Okay. So example 7, show that x minus 2 is a factor of px. So to show that, I need to say if x minus 2 is a factor of p of x, then Rx will equal 0, which implies P2 has to equal 0. So let's check P2 now. P2 is 2 times 2 cubed minus 7 times 2 minus 2. That's equal to 16 minus 14 minus 2. That's equal to 0. You've done the first part. If this is a 4-mark question, you've just got 2 marks. The first mark will be almost certainly allocated for just recognising you have to put a 2 in there. Probably writing that, or maybe doing this step here, where you substitute 2 in, will give you your first mark. Your second mark will be when you show it's equal to 0. Your other 2 marks will come from factorising. I'm going to shoot down now and just do that factorisation. And I might do it by just revising the division of polynomials idea with you. So now that I know that this is a factor, all I need to do is divide my original cubic by that. So I get x minus 2 dividing 2x cubed. There is no quadratic term, so plus 0x squared minus 7x minus 2. And I'll zoom in on this. So when I divide that, I start by dividing the first term by x, which gives me 2x squared. Multiply the 2x squared by the whole divisor, which is this bit. And I get 2x cubed minus 4x squared. And then do that subtraction. 2x cubed minus 2x cubed is 0. 0x squared minus negative 4x squared is positive 4x squared. And then I bring down the next term, minus 7x. X into 4x squared gives me just 4x. I multiply the 4x by my divisor again to give me 4x squared minus 8x. Negative 7x minus negative 8x is negative 7x plus 8x, which gives me x. I bring down the 2. I get x minus 2. X into x gives me plus 1. 1 times x minus 2 is x minus 2. I do the subtraction and get a remainder of 0, which is what I expected. But the nice thing here is that now I know that 2x cubed plus, I don't need that 0x, negative 7x minus 2 is equal to x minus 2 times 2x squared plus 4x plus 1. So I've got my p of x, d of x, and q of x, my quotient. And the remainder of x is 0. So I don't need to put that on there. Connor?
Could you also, you can factorise the quadratic as well?
I haven't gotten there yet, but yes, that's what we'll be doing next. Okay? So the next step will be, because it says in blue, fully factorise, means we have to take one more step. So in all likeliness, if this was a 4-mark question, achieving this is your 3rd mark, and then achieving that factorise is your 4th mark. And so I'm going to go through this process now, where I might just say, actually I'll do it down the bottom here, where, what is it, 2x squared plus 4x plus 1, 2x squared plus 4x plus 1. If you recall from last year, I'm looking for 2 numbers that multiply to give, 2 numbers that add to give. They need to multiply to give 2, which comes from my a times c, and they need to add to give 4. Anybody think of 2 numbers that do that? Okay, at this stage, I go, hold on a second. I don't think I can do this. Now, you might be missing something. If at the start of the question, though, you put it into the polynomial solver, which maybe I'll just quickly do now, or maybe somebody can do for me. Yeah, I'll do it on here. So I put it in the polynomial solver, and you should do this just to practice. That's f2. I put my original function in the polynomial solver, which has degree 3, a is 2, b is 0, c is negative 7, c is negative 7, and d is negative 2. And I solve that. A few side conversations going on at the moment, which is making it hard. I solve that, and it tells me there's a math error and tells me to start again. So I'm starting to feel the pressure a little bit, given that people are talking underneath me. And I do want to get through this, and it's really important that I'm up to date so you know what you need to know for your exam. When I solve that, I get 3 solutions, which is good. One of them is 2. The other 2 are negative 0.292 and negative 1.707. So there are 3 solutions. If I tested the discriminant of this quadratic here, I would get a positive discriminant, which is good, gives me 2 solutions. But the other 2 are irrational. So what does that mean in terms of factorization? It means that I really probably can't factorize it. So testing on GC gives me negative 0.292 and negative 1.707, therefore cannot be factorized, and that implies that this is our final answer. Sorry? GC graphics calculator. It's, don't listen to Lucas, it's graphics calculator. Okay, thanks ladies and gentlemen. Are there any questions on that? Dylan? Can I, sorry, say that again? Completing the square? I could do, but completing the square wouldn't give me a factor. So it would give me, basically, if I completed the square on this, I will get x minus 2 times by, and it will be 2, I'll just do it quickly, x plus 2 squared, but then that will give me an ancillary 4, so minus 8 there. Oh, and then I've got a plus 1, so minus 7, which doesn't really achieve factorising in the 3 brackets. So completing the square is great if you're solving and it equals 0, but not so good for when you're factorising. Any other questions? Okay, I'm going to leave this in your mind, the techniques for finding factors, and just talk about that slowly over the next week, because this will be important. So just some little things like with this question here, when you're playing with some of the questions in your textbook, start thinking about the easiest way to find factors. If you get a tech-free exam and you have to find a factor and you can't use your calculator, then you have to have strategies in place. So if I look at this one, if I put 1 into this, that 52 is going to outpower everything. If I put negative 1 in this, the 52 will outpower everything. There's no way 1 is going to make that equal 0. That's a strategy for me. Because of that 52, it's so large, 1's not going to work. And in fact, because x cubed is positive and 52 is positive, when I put in a number larger than 1, this thing is just going to get really, really big. So if I put in 2, that becomes 8 plus 52. That's not going to outweigh the 60. If I put in 3, 27 plus 52, that's not going to, none of that's going to outweigh the 79 that I get with the 27 plus 52. So now just do a couple of little strategies there. I've already determined, and this is all verbal by the way, so if you're not listening at the moment, you're missing this. Through those 2 strategies there, I've already determined that the factors of this are not negative 1 or 1, and they're also not positive. So straight away I'm just testing negative 2, negative 3. I'm trying to get this number, a negative cubed, big enough to outweigh that, which makes me suspect that maybe negative 4 is going to be big enough. Maybe negative 3 because of the negative 7x squared. And then I just go straight in and test those. P of negative 2, I'll just test that quickly, is negative 2 cubed minus 7 times negative 2 squared minus negative 2 plus 52, and that gives me negative 8 minus 28 plus 2 plus 52, which does not work because that's 36, 54 gives me 18, and then I could test P of negative 3, and I suspect negative 3 will be the one. I hope I've given you a question that actually works. Minus negative 3 plus 52. This is 27. This is almost goes too far. It is, I'm worried about this now. 63 plus 3 plus 55. So that's too far. So I actually don't think this one has any factors. A bad choice of questions. But anyway, can you see how I know there's a factor between these 2 now because this one's gone too far. That's negative 27. Negative 90 and 55 is negative 25. So it's gone from positive to negative. I know there's a root, there's a factor in between here. I don't know where it is, it's not going to be a whole number, but I know there's a factor in between. The strategies there, though, to take out the ones, take out the positives, will help you with factorising quickly. And just lastly, there are a couple of special cases that may come up in terms of factorising. I would just suggest that there's some questions on that in your textbook. So just be aware there's a couple of special cases, and when you get to those questions, practice using these, but they're going to be rare. You can see this, though. You can see if it's just literally x cubed and a number, that's the special case. And what do you have to remember? You have to remember the whole thing? Not really. But if you remember, if it's x cubed minus 27, where 27 is 3 cubed, then x minus 3 is a factor. That's going to get you all the way there. If it's x cubed plus 27, therefore x plus 3 is a factor, that's also going to get you all the way there. So that's it for the polynomial stuff. And I'm going to give you some time to practice that now, but I am going to return your formatives. So I'll stop this video now.